Dear students, today we'll see what do we mean by Zener diode. So we are going to see what is Zener diode. So if you see the symbol of Zener diode, it will look like this. It is up till here it is same like your conventional PN junction or diode. Then at this bar you have to just make it Z. You have to just make it a symbol of Z. This is Z type. So this is anode and this is cathode. And this is the symbol of your Zener diode. The speciality of this diode is it is a special type of PN junction diode. Special type of PN junction diode, and it is heavily doped. Okay. Now, because it is heavily doped, there are many characteristics in that which are very useful. Now, if you see a normal PN junction diode, say this is P-type material, this is N-type material, it is doped. P, these are electrons in N, this is a depletion layer, what we can get. So, this is plus minus depletion layer, what we can get. And if you apply a reverse bias for it, that is when negative of the battery is connected to the P-type region and positive of the battery is connected to N-type region, the majority charge carriers will repel and this depletion layer will increase. Okay. And then we see that the minority charge carriers of both the semiconductor materials, say for example electrons in P-type which are minority and holes in N-type which are a minority, they start crossing the junction, and once they go through this junction they collide with other atom bonds and there are many other charge carriers developed because of this collision. And because there is a large area over here, there is a collision, and because of the collision many electrons or many free electrons are developed, and in that process there is a large current which can flow, and that was called as our avalanche breakdown. Now here in a Zener, what we will see is we will see a PN junction same like your ordinary PN junction, P and N, and here you will see holes, and these holes in P-type area will be very heavily doped. There are many holes, it is very heavily doped. Similarly, electrons in N-type area, there are many electrons in N-type area, those are very heavily doped. These are very heavily doped. So here you can see this is very heavily doped, and the depletion region will be little thinner. Depletion region, that is this area, will be little thinner. It is little narrower as compared to your ordinary PN junction. So this is an important thing of this. Okay. So when you reverse bias a Zener diode, minus plus, minus go to the P-type region and plus goes to the N-type region. The minority charge carriers in P-type, say electrons, and minority charge carriers in N-type, say holes, they start crossover, and when they are crossing over, this depletion region area will be less as compared to the conventional diode. So there will be no collision of these charge carriers with the atoms inside, and there is no any free electron coming because of collision. But the atom bonds can be broken with the help of the electric field which is available in this depletion region. Because in a Zener diode, the electric field which is available will be more because the distance is less. Similarly, in PN junction diode, the electric field will be less because the distance is more. Okay, because we have in constant V is equal to a electric field multiplied by distance. So if distance decreases, electric field has to increase. And that is what makes a Zener diode to have a high electric field at the depletion region because of heavily doping. And this high electric field will make the atoms in the depletion region to break their covalent bonds, and it will give a free charge carriers. So there will be many free electrons which will be coming out, and because of that there will be a breakdown which will be called as Zener breakdown. Now that breakdown speciality is that this voltage and the voltage across this Zener diode what we get, whatever we apply and whatever voltage we get across the Zener diode, when the Zener breakdown occurs, when the minority charge carriers start flowing, there is large current flowing. At that time, the voltage across the diode will remain constant. And at constant voltage, there will be a large current flowing. Okay. And one more thing, because this breakdown is not because of collision, even if there is some heat produced, there will be no large heat produced. It will not destroy the device. Whereas in normal PN junction, because the avalanche breakdown was because of the collision, there was a heat produced, and that heat will destroy the diode if you increase the reverse voltage somewhat. That is not the case in Zener diode. Zener diode can work in reverse bias. It will give you variation in the current flow. Now, if you see the reverse current flowing, then you can draw a graph for that. If you see this graph, say this is voltage, this is current. The graph will show you there is a sharp breakdown. This is your breakdown voltage, and this is what current is increasing, and the voltage across the diode remains constant. Whereas the current is increasing, and there is no destruction of the device. There is no heat produced. There is no destruction of the device because this is Zener breakdown. Okay. Now, here what we see, this voltage is remaining constant at a certain level and current is increasing. Current can be increased or decreased at a certain voltage. That means this feature of Zener diode can be used to build a voltage regulator. So here the important thing to understand is that the breakdown was due to Zener breakdown, not because of avalanche breakdown.